You ever wonder how your phone can map out a cross-country road trip in just a few seconds? Or how the AI in a video game seems to perfectly anticipate your every move? Well, it's not magic. It's a process, a really systematic way of exploring possibilities to find the very best solution. So today, we're going to pull back the curtain on how computers think by digging into the fundamentals of something called search algorithms.
I mean, really think about it for a second. When you ask your GPS for directions, it doesn't just magically know the answer. It has to figure it out from millions, maybe even billions of possible routes. It has to search for the optimal one. So how on earth does it do that so fast without getting hopelessly lost? That's the exact puzzle we're going to piece together today.
The secret sauce here is a search algorithm. And to really get a feel for how they work, we're going on a little road trip of our own. We'll be using this classic map from AI research. Our mission, should we choose to accept it, is to find the best route from the city of Arad all the way over to Bucharest.
Okay, so before a computer can even start searching for a route, it needs a kind of mental map of the world it's playing in. And this involves two really crucial ideas that set the stage for everything else.
First up is the state space. Now that sounds a little technical, but it's actually super simple. It's just the collection of every single possible situation or state in our problem. For our road trip, the state space is literally the entire map of Romania. Every city, every road connecting them. It's the whole universe of possibilities.
But a computer doesn't look at the whole map at once. That'd be overwhelming, right? Instead, it explores specific paths, one after another. This branching set of paths that it actually considers is called the search tree. So don't think of it as the whole map, but as the specific route you're planning in your head, one decision at a time. So here's the bottom line. The state space is the world, and the search tree is our exploration of that world. And understanding that difference is absolutely key, because the strategy we use to build that tree, well, that determines everything.
All right, let's meet our first strategy. Imagine a very careful, super methodical explorer, someone who checks every single nearby option before they dare to take another step. This is the core idea behind our first algorithm, which is called breadth-first search.
The motto of breadth-first search, or BFS for short, is pretty simple. Don't get ahead of yourself. It explores the search tree level by level. It's like ripples spreading out in a pond. It checks all the paths that are just one step long first, then all the paths that are 2 steps long, and so on.
Okay, so our patient explorer is starting at Arad. The very first move it makes is to expand the city, which just means it looks at all the roads leading directly out. It finds paths to Sibiu, Timisoara, and Zarind, and it adds all 3 of those to its to-do list. And here's the most important part of this strategy. The explorer doesn't just pick one of those cities and start driving. No way. Instead, it methodically expands all of them, Sibiu, Timisoara, and Zarind, before it even considers taking a second step from any single one of them. It explores level by painstaking level. Now this super patient approach has a massive advantage. Because it checks paths in order of their length, it is absolutely guaranteed to find the shortest possible route. It's optimal, which is great, but it has a truly terrifying weakness. To do its job, it has to keep every single possible place it's ever considered visiting in its memory. And that memory cost? It's just staggering. For a moderately complex search problem, say one with 10 choices at each step, going 10 steps deep, BFS would need, get this, 10 terabytes of memory. That's more storage than most high-end gaming PCs have. The memory becomes a way bigger problem than the time it takes.
So, if our patient explorer is a total memory hog, what's the alternative? Well, let's meet its polar opposite. I like to call this one the impatient explorer. This strategy doesn't really care about being methodical. It just wants to find an answer and find it fast. This is depth-first search.
The motto of depth-first search, or DFS, is basically to go deep or go home. It picks a single path and just follows it as far as it can possibly go, hoping it just happens to stumble upon the goal. It's a really aggressive all-or-nothing approach.
So, starting from Arad, our impatient explorer might just randomly pick the road to Sibiu. Then from Sibiu, it immediately picks the next city, and the next, and the next. It just dives down one single branch of that search tree, completely ignoring all the other options back in Arad for now.
So what happens if that path turns out to be a dead end? Well, it just backtracks one step and then tries the next available deep path from there.
It never expands sideways like our Patient Explorer did. It just keeps diving, backing up, and diving again.
The payoff for being so impatient is an incredible efficiency with memory. It only needs to remember the single path it's currently on. But the cost is huge. It might find a solution, sure, but it's very unlikely to be the best one. And worse, if it happens to pick a wrong path that's infinitely long, it can get lost forever and never find a solution at all.
So what we have here are two fundamentally different explorers, right? One is patient, perfect, but needs a gigantic amount of memory. The other is fast, lean on memory, but, well, it's reckless and often wrong. And this sets up the central dilemma in designing any kind of algorithm.
This brings us right to the core trade-off. We evaluate algorithms on a few key things. Completeness, will it always find an answer if one exists? Optimality, will it find the best answer? And then, of course, time and space complexity. How long will it take, and how much memory does it need? And as you can see, there's no single winner. BFS is complete and optimal, but a disaster on space. DFS is amazing on space, but can fail on the other two big counts.
And there's another huge problem, especially for these simpler search methods. They can waste tons of time exploring paths that are just redundant. You know, like going from a rod to Sibiu, and then turning right around and going back to a rod. This quote from the source material just says it all. To search efficiently, you have to remember where you've already been so you don't repeat your mistakes.
So if both of our basic explorers are pretty flawed, what do we do? Well, in the real world, computer scientists don't just pick one or the other. They get clever, and they combine the best features of both to create these hybrid, much smarter algorithms. Take an algorithm called iterative deepening search. It's this brilliant hybrid approach. It acts like our impatient explorer doing a deep dive, but it only goes up to a certain limit, let's say 1 level deep. If it doesn't find the goal, it starts all over and does another deep dive, but this time 2 levels deep, then 3, and so on. You see this clever trick? It gives you the low memory usage of DFS, but because it's still essentially exploring layer by layer, it also gets the best answer guarantee of BFS. It is truly the best of both worlds.
And this isn't just theory. I mean, these fundamental ideas are the engine behind so much of the modern world we live in. They power your GPS navigation, they guide the AI characters in the video games you play, they solve massive logistics problems for companies like Amazon, and they even help scientists figure out incredibly complex things like how proteins fold.
So in the end, our little journey from Arad to Bucharest teaches us a really profound lesson about artificial intelligence. The real cleverness, the real intelligence, isn't always in just having the answer. It's in having a smart strategy for finding it. It's all about knowing how to search.